You ever take a paper clip and just bend it back and forth? It doesn't snap on the first bend, right? But keep doing it, and eventually it breaks. Well, it's not from one big catastrophic event, but from a slow, invisible weakening. That exact same force is at work all around us, in everything from mountains to machines. So today we're diving deep into the science of that relentless push and pull, cyclic impact.
So let's start with the big question here. Why is it that even the strongest things we build, the things that are meant to last, eventually break? I'm talking rock, steel, you name it. It's not always about some single massive blow. No, the real story is usually a lot quieter. It's a gradual process of a material just getting tired. All right, here's our game plan. First, we're going to define what that relentless push and pull really is. Then, we'll see how Mother Nature is basically the original expert at this. After that, we'll look at the rhythms of stress we create. We'll peek inside these materials to see how they get tired, and finally, wrap up with the really clever ways we engineer things to endure it all.
Okay, let's jump right in. Section 1, the relentless push and pull. It's time to put a name to this invisible force of wear and tear that is constantly at work. The big idea we're talking about here has a name: cyclic loading. And honestly, it's just what it sounds like. It's the repeated application of stress or force that weakens something over time. Let's go back to that paper clip. One single bend barely does a thing, but you bend it back and back again, and with each and every cycle you're adding a tiny bit of damage you can't even see. And then, all of a sudden, snap. No single bend was the killer. It was the repetition.
Now, what's so wild about this is that cyclic loading isn't just something that happens in a lab or a factory. Nope, nature is the original master of this stuff. Let's take a look at how the environment is constantly, and I mean constantly, testing all the materials around us.
Just take water, for example. Seems pretty harmless, right? But its power, when repeated, is immense. In colder places, you get these freeze-thaw cycles. Water seeps into a tiny crack in a rock. Then it freezes. And when water freezes, it expands, acting like a tiny, powerful wedge pushing the crack apart from the inside. Then it thaws, freezes again. You repeat that over and over all winter, and you can literally split a massive boulder. And then you've got wet-dry cycles. Some materials, like coal, actually swell up when they get wet and then shrink back down when they dry. This constant breathing, cycle after cycle, just progressively tears apart its internal structure, making it weaker and full of tiny holes.
And it's not just water. Temperature alone is a huge deal. Think about thermal cycling. Just a simple daily rhythm of heating up in the sun and cooling down at night causes something like granite to expand and contract. Over and over. It's a tiny movement, but it degrades its strength over time. And you can really supercharge this effect. Research shows that if you heat a material and then hit it with a blast of cold water, the impact failure is so much worse than if it just cooled down on its own. That sudden thermal shock is a killer, and it just dramatically intensifies the damage.
So, that's nature. But, us humans, we've become absolute experts at creating our own rhythms of stress. So let's look at how this very same principle applies to the world we've built all around ourselves.
We see this absolutely everywhere. Think about a bridge. It's not just sitting there holding weight, it's constantly humming and vibrating from traffic. That's a cyclic load. Engineers will literally simulate earthquakes shaking on walls over and over to test their endurance. Even high-tech stuff like hydraulic fracturing for energy, well, that's just using repeated pulses of massive pressure to crack rock deep underground. All of these are man-made stresses we either have to engineer for or create on purpose.
And get this isn't just some vague concept. It can get incredibly specific. For instance, in studies on coal, scientists found that one very specific vibration frequency, 75 Hz, was basically the perfect destructive rhythm. It caused the most damage to the coal's internal network of tiny pores. Now, why on earth does that matter? Well, because those pores are the superhighways for natural gas to travel through. If you damage them, it has huge implications for how we extract energy and even for mining safety. It just goes to show how a tiny constant vibration can totally change a material on a microscopic level.
Okay, so we've seen the forces, the natural ones and the ones we create, but what is actually happening inside the material when this is going on? How does something solid get tired and eventually break? Let's take a look inside the breakdown process.
This slide here lays it out perfectly. Failure isn't a single moment, it's a journey. See, it all starts on the left with an initial impact that creates some damage deep inside, totally microscopic, you never see it. Then, after more stress, you move to step 2, crack initiation. This is where tiny, invisible cracks start to form. Now we're at step 3, With every new cycle of stress, those little cracks start to grow and connect with each other. That's called propagation. And then, finally, all the way on the right, the damage hits a critical point, and bam, you get the final fracture. The break that you actually see is really just the very last moment of a long hidden story.
Here's another way to think about it, and it's all about energy. Imagine a brand new, solid wall. If you hit it, the energy travels through. That's a fresh material. But now imagine a wall that's full of tiny cracks. If you hit it, less energy goes through, right? More of it bounces back at you, and the energy that does go in just makes the cracks bigger. That's exactly what this quote is saying. As the damage builds up, the material gets worse and worse at letting energy pass through it. So more energy gets reflected, and the rest gets absorbed as new damage. It's like the material forgets how to handle stress and just starts to fall apart from the inside.
So, what's the tangible result of all this? This chart sums it up beautifully. As that cyclic damage keeps building, the material's key properties take a nosedive. Its hardness, that goes down. Its overall strength, that's reduced. And at the very same time, its porosity, which is just the number of tiny holes and gaps inside it, goes up. The material literally becomes weaker and more brittle from the inside out.
Okay, this is all really cool science, but so what? Why does any of this research actually matter? Well, it's simple. If we can understand exactly why things break, we can build a world that's designed to last. And that brings us to our final section, engineering for endurance.
And this, right here, is the big payoff. We don't study failure just to know about it. The entire point is to get ahead of the problem. By understanding the nitty-gritty of how things break down, we can design totally new materials and much smarter structures from the ground up, ones that are built specifically to absorb and get rid of that repetitive energy, instead of just letting it build up as damage.
And the real-world applications for this are just huge. This research leads directly to safer buildings that have walls designed to flex and absorb an earthquake's energy instead of just cracking and falling apart. It means we get more durable roads that can handle endless freeze-thaw cycles and the pounding of traffic. It even leads to these incredible new things like metal rubber, a material designed from the start to just soak up repeated impacts. See, understanding why things break is always the first step to building a world that does.
So, I'll leave you with this one last thought. Just look around you right now. The chair you're sitting on, the floorboards under your feet, the phone or computer you're watching this on. After everything we've just talked about, what in the room with you right now is being slowly, invisibly weakened by a relentless cycle you can't even see? Once you start thinking about it, you start seeing it everywhere.